Hi, welcome to Marine Gurukul video series. In this video, we shall cover the first part of Great Circle Sailing. This video shall cover calculation of Great Circle distance, initial course and final course with reasonable number of numericals also covered in the video. Let us start the discussion by having an overview or revising the concept of great circle. A great circle is a circle on the surface of a sphere whose plane passes through the center of the sphere. So any circle drawn on the surface of a sphere whose plane passes through the center of the sphere shall be referred to as a great circle. If you see this diagram out here of a sphere on which three great circles have been drawn, and you can see the plane of each of them passes through the center of the sphere. A great circle is the largest circle that can be drawn on any sphere, means the radius of the great circle is the largest possible for any circle that can be drawn on the surface of the sphere. Any diameter of any great circle coincides with one of the diameters of the sphere. All great circles have the same center and radius as each other, as well as that of the sphere. So that means radius and center of every great circle is same as the radius and the center of the sphere. For any 2 points on surface of a sphere, there shall be one and only one great circle passing through them. It means that if you take any 2 points on the surface of a sphere, there shall always be one great circle passing through them, and that shall be the only great circle. That means one and only one great circle passes through any 2 points given on the surface of the sphere, unless the exceptional condition is met. And the exceptional condition is if the pair of points or the points happen to be diametrically opposite to each other, that also referred to as antipodal points, then in that case through those 2 points you can draw infinite number of great circles. The minor arc of a great circle between 2 points is the shortest surface path between them. So if you travel along the surface of the sphere, then the arc along the great circle or the track along the arc of great circle shall be the shortest distance between any 2 points on the surface of the sphere. Now let's discuss why great circle distance is the shortest distance between any 2 points on the surface of the sphere. We know that the surface of the sphere is curved. So any 2 points on the surface of the sphere cannot be joined with a straight line along the surface, because surface being curved. So that means they have to be joined by an arc. Now we also know that as the radius of the arc increases, its curvature decreases. Decreasing curvature means the arc is tending closer to the straight line. So if you have an arc with the least possible curvature, then obviously along that arc the distance shall be shortest. And we have already said that the largest possible radius of a circle on the surface of a sphere is that of a great circle. So if that is the circle with the largest possible radius, means it's a circle with minimum possible curvature, and hence the distance along a great circle between any 2 points on the surface of the sphere shall be the shortest distance as far as surface movement is concerned. Now let us quickly review the concept of spherical triangle and the formulae used for solving the spherical triangle to the extent as required for a topic. A spherical triangle is a triangle on the surface of a sphere. So please remember, it's a triangle on the surface of the sphere, every side of which is an arc of a great circle. That means if I have three great circles intersecting each other, and if the sides form a triangle where on the surface of the sphere, the triangle so formed is referred to as the spherical triangle. As you can see in this diagram, this gray shaded triangle is formed by intersection of this great circle, this one great circle, and the red great circle. So this is one of the spherical triangles so formed. Now, since it's a triangle, It has 6 parts. It has 3 angles at the vertices, and it has 3 sides. So how are these parts of the spherical triangle identified? The vertices, the names of the vertices indicate the name of the angles at the vertices, and they are represented by capital alphabets. For example, in our case, if you see on the screen, you have X, Y, and Z which have come, and these are the vertices of the spherical triangle. And obviously then this angle at this vertex is referred to as angle X, angle Y, and angle Z. Now the spherical triangle also has 3 sides. Now these 3 sides are the sides opposite to the angles. Sides are either named like XY, YZ, and ZX, or they are represented by small alphabet, same alphabet in lowercase as the one used for the opposite angle. So that means side XY is nothing. Either you can say side XY or you can represent it with small z, as you can see in the diagram. Side YZ, you can represent it by small x, and side XZ you can represent by small y. So you can represent the sides either by using the combination of the vertices, or you can use them the opposite angle in the lower case. Now cosine formula is the formula which will be used for solving questions in this part of the video that we are covering. Now what is cosine formula? I'm sure all of us know it, but let's quickly review it. Cosine formula is used for any side. So cosine of any side, x, y, or z, any of these sides, is equal to cosine of the opposite angle into sine of adjacent side 1 into sine of adjacent side 2 plus cosine of adjacent side 1 into cosine of adjacent side 2. Now let's write down the formula for all the 3 sides. Let's say if we write it for cosine x, if we write for the side yz or small x, then opposite angle would be x, adjacent sides would be y and z, and the above formula then can be written like cos x is equal to cosine of angle x into sine of side y into sine of side z plus cosine of side y into cosine of side z. The formula can be written again for cos y, and for cos y obviously opposite angle is capital Y and adjacent sides are small x and z. Similarly for cosine of z, opposite angle would be z, adjacent sides would be small x and small y. Now what do we see in this cosine formula which we have just learned here and revised in fact out here, is that it involves 3 sides and 1 angle. So to be able to use the cosine formula, you need to know either all the 3 sides, then the cosine formula can be used to find the missing angle, or you should have 2 sides and the included angle. In that case, you can use it to find the third side. So please remember, to be able to use the cosine formula, either you should have all the 3 sides or you should have 2 sides and the included angle. Now let us take this great circle concept that we have learned onto surface of the earth, and let us just review or discuss the features of great circle tracks on the surface of the earth. The great circle track between 2 places implies, if we have 2 places on the surface of the earth and we are talking of GC track between them, it means we are talking of the smaller arc of the great circle passing through the 2 positions. What does it mean? You can see in the diagram, we have the surface of the earth, we have the 2 poles, north pole and south pole, equator also showing up. Then you have position A, then you have position B on the surface of the earth, and now you have this great circle passing through A and B, because we said unless the points are diametrically opposite to each other, you will have one and only one great circle passing through them. Now in this great circle, there are these 2 points divide the great circle into, one is the smaller arc and the other is this bigger arc. So whenever we talk about the great circle track, we shall talk about the smaller track smaller arc, and you can see which is now being shaded in red. So the GC track between A to B or B to A shall be this arc of the great circle, that is the shorter arc. The GC track is always curved with its convex side pointing towards the pole as follows. Now when you move along the GC track, it is along a curve on the surface of the earth, and the curvature, the convex side of that curve, is always pointing towards the pole. Now the question is, we have two poles, North Pole and South Pole. Towards which pole does the track curve and present its convex side? Now if both the positions lie in the same hemisphere, that means arrival and departure positions are either in both in northern hemisphere or both in the southern hemisphere, the convex part shall be towards the pole of the hemisphere in which both the positions lie. For example, you can see in this diagram, if A and B lie in the northern hemisphere, the great circle track between them will have its convex part pointing towards the north pole. You can see the other diagram here. If A and B lie in the southern hemisphere, both of them, then the great circle track shall have its convex part curved towards or presented towards the southern pole. Both positions lie in the opposite hemispheres. That means the departure and arrival positions do not lie in the same hemisphere. Then the track shall curve and present its convex part towards the pole of the hemisphere in which the position has the higher latitude. Whichever of the two has the higher latitude, that particular pole would be the pole towards which the convex part of the curved track shall be presented. You can see in this diagram we have position A in the northern hemisphere, we have position B in the southern hemisphere. Needless to say, latitude of B is higher than the latitude of A. So the track between AB or BA is curved towards the southern pole because the southerly latitude is higher than the northerly latitude. Now there can be a situation in which both the places lie in opposite hemispheres, but both positions have the same latitude. In that case, the great circle track shall be somewhat like this. In their respective, so the track in the northern hemisphere will have its convex part towards the north pole. The track in the southern hemisphere shall have its convex part toward the southern pole, and in this case both A and B are equal in value but opposite in names. So the great circle track between A and B shall be somewhat like this, what you are seeing in the diagram. Now great circles questions can be easily handled if we follow certain definite steps like a drill. So the steps involved in solving the great circle sailing questions are: first we need to plot or mark off the departure position, and in relation to the departure position we need to mark off our destination positions. So if I wish to call the departure position as A and destination position as B, then I need to mark off B in a relatively correct place with respect to A. What does it mean? It means that depending on the DLAT from A to B, we decide whether B would be marked north or south of A. So if DLAT is north from departure to destination, then B is marked north of A. If DLAT is south, B is marked south. Likewise, we evaluate the D long from departure to destination, that is from A to B. If D long is east, then B is plotted east of A, and if D long is west, B is plotted west of A. So therefore, based on names of DLAT and D long, we mark off position B with respect to position A. Then we make the spherical triangle with appropriate pole. Now appropriate pole here means the pole towards which the great circle track shall present its convex part. So we have already dealt with as to which side or which pole would the convex part be presented, and to whichever pole we expect the convex part to be presented, that shall be the appropriate pole as far as making this diagram is concerned. Then we get a spherical triangle whose vertices are the pole, position A and position B, PAB triangle. The three sides of the spherical triangle are then PA, which is arc of meridian of the departure position from pole to A, PB, arc of meridian of destination position from P to A, P to B, I'm sorry, and AB, the arc of great circle track contained between A and B. Now we have to load these parameters as we calculate onto the diagram or the triangle that has been made. Now drawing an appropriate spherical triangle and loading with given parameters can be seen in this small illustration. We have the sphere of the earth. We have the equator of the earth showing up. If I have this as the equator, I have the north pole, I have the south pole marked. Now, if I have to take two positions, a position A out here in the diagram, and I take position B, which is position here, then I can draw the meridian of A, which comes up here. Likewise, we can draw the meridian of B, that's the B. Now we draw the arc of great circle that passes through A and B. Now this is the arc of great circle which passes through A and B. Now we have this spherical triangle which is formed by PAB. This is the spherical triangle of interest to us. Now in this case, this is the GC track from A to B. Now this green shaded arc is the arc of meridian of A from P to A. Up to equator, we all know it's 90 degrees. From equator to A, this arc is equal to latitude of A. So therefore, this side becomes 90 minus latitude of A. Exactly the same way, PB becomes 90 minus lat of B. So now in this triangle also, this is the meridian of A and this one is the meridian of B. So if I know the longitudes of A and B, then this angle becomes D long between A and B. So this angle is the D long from A to B in case I'm going from A to B, and it would be D long from B to A if I'm going from B to A. So now in this spherical triangle, if I know the coordinates of the departure position, I can get the latitude, this side B, PA. If I know the coordinates of B, I can get this side PB. And if I know the longitude of A and B, I can get angle P. In other words, I can get the two sides and the included angle. Now having drawn the PAB triangle, having transferred the available information onto the triangle, we are ready to solve the triangle. We solve the triangle using the cosine formula, and in solving so, the side AB of the PAB triangle that we shall obtain when expressed in minutes of arc shall be the great circle distance between A and B in nautical miles. I repeat, AB when expressed in minutes of arc shall be the GC distance between the two positions. Again, we can solve for angle A of the PAB triangle. Please note that angle A shall be the internal angle of the spherical triangle PAB, and this angle A can be used to evaluate the initial course of the vessel. Angle B of the PAB triangle, the internal angle again, can be calculated and used to evaluate the final course of the vessel. How do we evaluate initial and final course using angles A and B? We shall just list down few steps and then see the same or apply the same to few illustrations to understand this issue. First, in the PAB triangle, we shall identify the direction of north at A and north at B, which shall be the northward direction of the meridian, respective meridians of A and B. Then courses, we all know, are measured clockwise from true north up to the ship's head and expressed in three-figure notation. Let's take this example. We have the North Pole out there on the screen. We have position A out here. We have position B coming in here. These are the meridians of A and B. And then we have the GC track between A and B. Now, in this, A is the departure position, B is the destination position. When you solve the PAB triangle, you shall be getting this as angle A and this shall be angle B. Now, when the vessel sets sailing from position A and reaches position B, the vessel shall be placed at A the way you see in the diagram. When she reaches B, she shall be placed the way you see it here. Now you can see in this case, what will be the direction of the north at A? This will be the direction of north at A. This shall be the direction of north at B. Both these are shown as N in the diagram. Now from this, if I measure clockwise up to the ship's head, this shall be the initial course out here, which is represented by the blue arrow. So this represents the initial course, which we see that angle A and the initial course happen to be same. Now when the ship reaches at B, again from the north, we go clockwise up to the ship's head, and this blue arrow represents the final course. But when you solve the triangle, you are not getting this angle. What you are solving is internal angle B. So we can see in this case, the final course shall be 180 minus angle B. In this case, initial course is equal to angle A, and the final course is 180 degrees minus angle B. So this is how A and B are used to evaluate initial and the final courses. Let's look at another example then. Here is the North Pole. Again, position A, position B, meridian of A, meridian of B, great circle track through the two. Please note the great circle track is curving towards the, or presenting its convex part towards the North Pole. Now in this case, angle A, calculated angle A would be this one and calculated angle B would be this much. Let's place the ship both at A and B. Let's mark the initial course at A clockwise from true north. I'm sure you'll all agree with me that the blue arc represents the initial course. What we have calculated is this angle, and it's very evident from the diagram that the initial course shall be 360 degrees minus the calculated angle A. Let us now mark off the final course at B clockwise from north. I'm sure you'll agree with me, clockwise from north up to the ship's head is the final course. What you have calculated is this as angle B. This angle B out here shall be equal to this angle. Why? Because they are vertically opposite, and this final course then would be 180 from here to here plus angle B. So in this case, the initial course is 360 degrees minus angle A, and the final course is 180 degrees plus angle B. Let's just take one more example. We have the southern pole in this case. We have position A, position B, meridian of A, meridian of B, and we have the GC track from A to B. Please note, it's presenting its convex side to the southern pole now. Angles, when you calculate, this would be the angle A that you will obtain, and this shall be the angle B you will obtain. The north direction at A would be represented by this side, and this would be the north direction at B. So let's mark the north directions and place the vessels at both A and B. Now let's mark off from north clockwise up to the ship's head the initial course. You can see this blue arc out here. This represents the initial course. And what do you see in this case? This is angle A. From here to here is 180 degrees. So the initial course shall be 180 degrees plus angle A. Likewise, let's first mark off the final course at B. Final course at B shall be this one. What you have calculated is this angle B. This angle B is equal to this one, which is vertically opposite. And what do we see? Final course is 360 degrees minus angle B. So in this case, the initial course is 180 plus angle A, and the final course is 360 degrees minus angle B. With these couple of illustrations, I'm sure now you'll be able to get initial and final courses having calculated the internal angles A and B of the PAB triangle. Now let us apply what we have learned in solving some questions. Calculate the great circle distance, initial and final course from point A 10 degrees north, 40 degrees east to position B 30 degrees north, 100 degrees east. So the first thing we need to do is make PAB triangle, for which it is important that we place positions A and B in relatively correct orientation and also identify the appropriate pole. Now we see D-lat from A 10 degrees north to 30 degrees north is A to B is 20 degrees north. D-long from A to B, that means 40 degrees east to 100 degrees east, is east. Therefore position B lies to the north of A and to east of it. A and B both have northerly latitude, so obviously the PAB triangle shall be made with the northern pole, so that is the appropriate pole. So now we get going with the drawing of the PAB triangle. Here is the north pole, then we mark off position A here, position B to the north and to the east of it, north and east of it. We draw the meridians of A and B. Now we have this angle at P, which is the D long between A and B. Now we draw the GC track from A to B. This represents the GC track from A to B. Now vessel, when it departs from A, shall be positioned as shown here. When the vessel reaches B, it shall be placed like this. Now, knowing the coordinates of A and coordinates of B, we can get the value of PA, PB and angle B. I'm sure we all know that PA is colat of A, so it is 90 minus latitude of A, it is 80 degrees. Likewise, PB is 90 minus latitude of B, 60 degrees. And angle P is the D long between A and B, which is again 60 degrees. So now we have loaded all the known information onto this diagram, and now we are ready to use our cosine formula. We write the cosine formula for side AB, which is the GC distance from A to B. So this is the cosine formula for side AB. We know angle P, we know side PA, we know side PB. We put all these values and this gives us the value of AB as 59.119 degrees. When multiplied by 60, it translates into 3547.13 minutes, which is the GC distance between A and B, 3547.13 nautical miles. Now we write the cosine formula again, this time for angle A. And this is how the cosine formula for angle A shall be written. Now we know all these parts used on the right hand side, including AB, which has been just calculated to be 59.119 degrees. When we put all these values in the formula, we get the value of A as 60 degrees 54.8 minutes. That is this angle. Now we go to the PAB triangle and mark off the initial course clockwise from true north at A. Now this blue arc which has just come up represents the initial course of the vessel at A. And what do we see? This initial course is very much the same as angle A. Therefore, the initial course is equal to angle A, but now it's represented in three figures. Please note 0, 6, 0 degrees, 54.8 minutes true. Now we write again the cosine formula for angle B. We know all these parts on the right hand side. We put their values and we get the value of angle B as 96 degrees 24.6 minutes. So this angle is 94 degrees 24.6 minutes. We go to the PAB triangle and mark off the final course clockwise from true north at B up to the ship's head. I'm sure we'll agree that this represents the final course. And what do we see in the diagram? The final course is 180 minus calculated angle B, and we come here, the final course is 180 minus B, which is 083 degrees 35.4 minutes true. So now we have the GC distance, we have the initial course, we have the final course. We summarize our result here, and that's how we can use what we have learned to solve these problems which need us to calculate the GC distance, initial course, and the final course. Let's take another example. Find the great circle distance, initial course, final course by great circle sailing from position A 20 degrees south, 165 degrees west to a position B 35 degrees north, 155 degrees east. Now in this question we see that the two latitudes are in different hemispheres. Position B has higher latitude, so appropriate pole for PAB triangle shall be the northern pole. D-lat from A to B, 20 degrees south to 35 degrees north. Obviously D-lat is north, so B would be north of A. Now D long, the shorter arc from 165 degrees west to 155 degrees east, we know would be in the westerly direction. That means it shall be 40 degrees west. D long from A to B, if you calculate, if you have any doubts, you can write in your rough notebook and calculate. D long from A to B is 40 degrees west. That means B shall lie to the west of A. So that means B will be north of A and to the west. And since the northerly latitude is the higher latitude, we shall make it with the northern pole. The appropriate pole shall be the north pole. So let us make the PAB triangle based on this discussion. Here is the north pole which comes up on the screen. B would be to the north and west of A. So we first put A on this side. So B would be north of A and also west of it. We draw the meridians of A and meridian of B. We draw the GC track from A to B. So this is the GC track from A to B. We place the vessels as oriented at A and at B. And now with coordinates of A and B known, we can calculate PA and PB and also angle P. Now as far as PA is concerned, we have chosen the northern pole. So latitude of A is 20 degrees south. The arc of this meridian shall be 90 degrees up to the equator and another 20 degrees south of it. So that means PA in this case would be 110 degrees. So PA is 110 degrees. PB would be 90 minus 35, that is 55, and angle P will be the D long from 165 degrees west to 155 degrees east, that is 40 degrees. Now having made the triangle and loaded the information, now it's only a matter of applying the formula. We write the cosine formula for side AB. We know all the parts on the right hand side. We put their values and we get AB as 66.828 degrees, which translates into 4004.69 minutes. That means great circle distance from A to B is 4009.69 nautical miles. We write the cosine formula again, this time for angle A. Obviously angle A would be this angle out here. So when we calculate angle A by putting the values, including using the AB calculated above, we get the value of A as 34 degrees 56.5 minutes. So this angle is 34 degrees 56.5 minutes. We mark off the initial course at A clockwise from north at A, and I'm sure we'll agree that this represents the initial course. And now it leaves no doubt. The initial course is equal to 360 minus calculated angle A. So the initial course shall be 360 minus angle A, that is 325 degrees 03.5 minutes true. We rewrite the cosine formula now, but this time for B, and we put the values and we get the angle B, which is this angle, as 138 degrees 55.6 minutes. Now in the diagram we mark off the final course clockwise from true north at B. I'm sure we'll agree this will be the final course. Now obviously this final course is arc from here to here is 180. So this shall be 180 plus angle B. So we get final course as 180 plus angle B, that is 318 degrees 55.6 minutes true. We summarize our answers: GC distance, initial course and final course. Now this one has been specially taken because here the vessel is moving across the 180th meridian, so you have to be careful. Though vessel started from westerly longitude, arrived at easterly longitude, but D long was west. Why? Because the vessel moved in the westerly direction, crossing the 180th meridian. Also please pay attention here, PA was 90 plus latitude and not 90 minus latitude. So this has been specially picked up to highlight these two factors which you need to take care of when you make a PAB triangle and you load it with information. Now let's have a look at a slightly different example. A vessel sailed on an initial GC course of 210 degrees true from position 38 degrees 30 minutes south, 025 degrees 30 minutes west for a distance of 1000 nautical miles. Find the latitude and longitude arrived and the final course. Now in this case we need to make a PAB triangle. So since we are starting from a southerly latitude, and in this case incidentally also the course is in southwest quadrant, so in all probability the final position shall also be in the southern hemisphere. However, my argument for choosing the southern pole for making the PAB triangle is only based on the fact that the initial position is in the southern hemisphere. As I do not know the latitude of the position arrived, therefore I'm just making the PAB triangle with southern pole because I'm starting from my starting latitude happens to be in the southern hemisphere. When I get the value of PB, that shall help me in knowing whether the arrived position is in the southern hemisphere or the northern hemisphere. So let's make a diagram. We take the southern pole, we mark off A and its meridian, so that is position A with its meridian. Vessel is placed at A, heading 210 degrees, her initial course. So her GC track shall be with initial course of 210 degrees true, passing through A. So this represents the GC track. And the initial course is shown on the diagram, that's 210 degrees true. Now when the vessel travels along this track through 1000 miles, now 1000 miles divided by 60 becomes 16 degrees 40 minutes. It will bring us to a position B. So position B is there. We draw the meridian of B, and when vessel reaches B, she shall be placed as you can see out here. Now in this diagram, this angle A you can see here shall be 210 minus 180. So angle A we know is 30 degrees. We know the latitude of A, so we can get PB, which we all know by now. It's 51 degrees 30 minutes. We know AB is 16 degrees 40 minutes. So we have two sides and the included angle. We can apply the cosine formula to calculate side PB. So the cosine as per cosine formula, PB shall be equal to this expression. We know all these parts. We put their values and we calculate the value of PB as 37.744 degrees. Now this PB value, if it's less than 90 degrees, that means position B is in the southern hemisphere. Had this value been more than 90 degrees, that means B would have gone to the northern hemisphere. So I'm again repeating that our argument for starting the PAB triangle with southern pole was purely because the starting position was in the southern hemisphere, and I am not, though we could guess that B would also be in the southern hemisphere, but that was never the argument taken in deciding to make the PAB triangle with the southern pole. So now if PB, which is the colet of B, is 37.744 degrees, so 90 minus PB gives us the latitude of B, which is 52 degrees 15.3 minutes south. Now we work towards calculating angle P. So we write the cosine formula for angle P, which includes the use of side PB, which has been calculated just now. So we put all those values and we get the value of P as 13 degrees 32.9 minutes. 13 degrees 32.9 minutes is the D long from A to B, and as you can see in the diagram, the D long is west. So the D long from A to B is 13 degrees 32.9 minutes west. So applying this D long to the longitude of A, we can get the longitude of B, and which is 039 degrees 02.9 minutes west. So we have now got the coordinates of position P as 52 degrees 15.3 minutes south and 039 degrees 02.9 minutes west. Now we write the cosine formula to get angle B so that the final course can be evaluated. We write the formula for cosine B, we put the values, and we get the value of B as 140 degrees 16.1 minutes. That is this angle. On this diagram now, we mark off an arc representing the final course clockwise from north. This is the final course at B. And now we can see that final course will be equal to 360 minus angle B. Why? Because this angle is vertically opposite to B. And so therefore we can get the final course as 360 minus B as 219 degrees 43.9 minutes. So now this way we have been able to get the latitude of latitude of B, longitude of B, as well as the final course. Now we come to an end of Great Circle Sailing video 1. I'm sure by now you would be reasonably comfortable with the concept of calculating the GC distance, initial and the final course. If you have any feedback or you need any further support, please reach us on marinegurukul@gmail.com. If you like our effort, please do subscribe to our channel for automatic notification of our upcoming releases. Thank you very much for watching Marine Gurukul video series. Thank you once again.